I think we should start the recording. Yeah, thanks.
Okay. And is there background noise or can you hear me well?
Uh, no, there is no background noise, but the voice is a bit soft. So
Okay, I'll come closer. Yeah, sorry, my video may not look very good, but I will be closer to the mic.
yeah, now the voice is pretty good.
Okay, great. All right. Good evening, everyone. This is Professor Amit Sethi from Indian Institute of Technology.
Hey, sorry, Amit.
Yeah,
Do you have microphones that you could use?
yeah, I can. Just give me a
Yeah.
second. Is this better?
Yes, it is
Hello,
better. Yes, it is better.
Dr. Professor Avinal, can you hear me?
Yes, I can hear you. Can you hear me?
Hello. Okay, I cannot hear anyone. All right, let me quickly check. Okay, great. All right. So shall I get started?
Yes, please.
Okay. Good morning, everyone, and good evening, everyone, depending on your time zone. I am Amit Sethi. I'm a faculty member at Indian Institute of Technology, Bombay. I do my research mostly on medical images with medical researchers as my collaborators. And within that, specifically, I work on cancer pathology images, and we work on problems such as detecting cancer, grading cancer, finding molecular mutations in cancer because different mutations have different uh, specialized treatments and so forth. So those are some of the things that we work on, and specifically we concentrate on imaging modalities that are cheaper to acquire, so that the cost of precision diagnosis can be brought down in both low and middle income countries as well as in across the world. So I work with Tata Memorial Hospital in Mumbai and University of Illinois in Chicago and King's College London in London. These are my three primary collaborators, some of the researchers there. And because of that, we deal with problems such as few shot learning, weakly supervised learning, semi-supervised learning, because these cancer images can be sometimes very large in size, but you may have not very many patients whose data may be available. So today in ESWEEK, I will talk about few shot learning for images, and then my PhD student Abhijeet, he is going to talk about, he will give you a demo, and hopefully he can show you how some of that can also work on embedded systems such as a Jetson Nano. So first, let me get into the theory and some of the details of the techniques that are used for few shot learning. And then what we will do is we will get into a demo after that. All right. So at any point, if you have questions, please feel free to stop me and ask me the question. So uh, The outline is that I will first talk about what is few shot learning, why it is important, and when you are coming up with a new technique, if you want to compare it against existing techniques, then what are some of the benchmark data sets, what are some broad set of approaches, and then we will go into some techniques. I will cover some of the techniques that are listed here. So when we talk about deep learning, what deep learning actually is basically deep neural networks, which is a type of machine learning, except that here we don't uh, program computers to extract handcrafted features. We let the layers of the neural network extract the features themselves. So features and then features of features and so forth. And so if you have a lot of data, then these deep neural networks do very good job of driving the generalization up, driving the classification accuracy on unseen data up and so forth. However, this requires a lot of data. So these deep learning techniques are quite data intensive, and they are also computationally very intensive. So these deep neural networks can have tens of millions of parameters. Now there are actually pushing billions of parameters. So because of that, even just a forward run through deep neural network can require uh, trillions of floating point operations, or at least billions. And then if you want to train the neural network, all the parameters of the neural network, all the weights and biases, then it can require 10 times as many computations as the forward pass, for example. So it's quite computationally intensive, and then it can overfit very quickly on domains with less data. What that means is that, let's say if you have disease A versus disease B classification, and you have only 100 images of disease A and 100 images of disease B, it is very easy to get 100% classification accuracy on the training data, but that doesn't mean you will get good accuracy on testing data or the validation data which is held out. So that's what basically what overfitting means. Any questions? All right. So basically, one of the remedies to not having enough data is few shot learning. There are other ways of dealing with less data also. But the way we will define few shot learning is that we want to train the best possible model in terms of accuracy, but we will use only k samples per class. So let's say if you have C classes, so what that means is, let's say you have uh, C is equal to 3, right? So that means you have three classes such as normal tissue, and then you may have benign tissue, which is uh, not cancerous, uh, but it is not normal either. So you may have benign tissue, and then you may have cancerous tissue. So these would be like three things that we want to classify, right? So you have benign, and then you have cancer, right? So that could be three different classes, but you have only k different images of each class. So k, for few shot learning, usually we take the definition that k is less than equal to 5. Uh, when k is larger, let's say k is 50 images per class, then we will call it low shot learning. So compare that to an ImageNet dataset, which a lot of you might be familiar with. In ImageNet dataset, you have C is equal to 1000. So you have 1000 different classes, and then your K is also equal to 1000. So you have a total of 1 million images. So for each class, you have 1000 training samples to train on. But here, what we have is K is less than equal to 5. Okay, and C could be, let's say, 20 different classes. So one of the extreme cases of that is K is equal to 1. So what that means is that you have only one example per class, and that one example is very difficult to learn from. And then even more extreme cases, K is equal to 0, which is called zero shot learning. And that may not even be possible, that you don't even have an example of that class at all. But the way it works is that you don't just have you may not have any image of that class, but you may have a text description. So what that requires is that your pre-training requires images as well as text descriptions. So this is out of scope for us. We will not be talking about this in this lecture, in this talk. We will be concentrating on few shot learning. Now, few shot learning in vacuum is not very beneficial, which means that you cannot simply go ahead and do few shot learning just starting from scratch with 5 samples per class. That's very difficult to do. If you think about how human beings recognize objects, so let's say you are learning about a new species of animal, right? And I give you only like 2 3 examples of images of that animal, you are good to go. You know now how to recognize that new animal that you have not seen before. For you, the K is equal to 2 or 3. Uh, but that doesn't mean that you were just born and you were given 2 images of that animal. There is 10, 15, 20, 30 years of image training that you have gone through, whether you know it or not, vision training that you have gone through to come to this level where when I show you 2 or 3 images, then you are ready to recognize that new class with just 2 or 3 examples or even one example. So there's a lot of background knowledge that you have about what makes a shape, what kind of texture patterns to look at, what kind of colors to look at, and so forth. So basically, we can use a lot of source classes, right? So basically, what that means is that we may have a large data set of other objects and their classes that are given to us that we can utilize. For example, the ImageNet data set. And now we want to transfer that knowledge to learn about new images with in the few shot learning scenario. Alright. So the broad strategies for few shot learning would be that you will take a deep neural network and you would take one of these 3 paths or perhaps a combination of the 3 paths. So the first broad path or the broad strategy is that you have uh, you have a data-driven approach. Okay, so what data-driven approach means that you have less data, but you will try to utilize it to the maximum by doing something called data augmentation. Or what you might do is you might use unlabeled data. What that means is that you may have a large set of photographs which do not have labels. You have a large set of images that do not have labels, but somehow you can learn the distribution of uh, or the or the probability joint distribution of all the pixels that are there in some sense or some functions thereof, so that you can restrict your search in extracting features that you will use for classifying new classes with few samples. So let me give you an example of data augmentation. Yes. So what I mean by data augmentation is that if you look at, for example, this image of a Chihuahua dog, right? And let's say my task is to recognize dog breeds, right? So this is one image, but what I can do is I can create several different versions of this image that still look like a Chihuahua dog. So if my task is to classify between different dog breeds, I want to retain the essence of that breed, but change it slightly. So, for example, make the dog a little taller or a little wider or slightly different color. Uh, so I'm using the same image with slight variations. Uh, but I know that if I have 100 different dog breeds, it is still one of those 100, which is the Chihuahua dog. It's not a different breed. It's not an Alsatian. It's not a poodle. It's not a Pomeranian. It's still a Chihuahua. So how I do that is that in many of the vision libraries or deep learning libraries, you will find something called transforms of images. And these transforms of images could be something as simple as shearing the image. So you shear the image slightly to the right or to the left, or you change the colors of the image slightly by changing the brightness or the contrast or the saturation of the hue a little bit. You have to be careful about changing the hue because in some problem domains, the hue is very important. The dog should not look green, or if you're looking at a cancer tissue, it should always hematoxylin and eosin diet. Cancer tissue should always look pink and purple and not blue and green. So you have to be careful about how you use these transformations, but you can use them if you know how you are using them. So you can also do things like horizontal flipping. Horizontal flipping you can do because the same dog looks, it's the same dog breed if you look left to right or right to left. But in radiology, for example, if you're looking at a chest X-ray, you may not want to do a horizontal flip because the the heart always appears on one side of the screen, for example. So you use these transformations based on your knowledge about the image domain. And I want to show you one transformation that this is slightly different from the image that I saw before, but it is still a very, very much a Chihuahua. I can run this again and have a random transformation, right? It will look slightly different image. And that's how I can increase the number of data points that I have, which is the number of images that I have for a particular for a particular problem, right? So I can keep running this until I get new images and so forth. So coming back to my presentation here, so that is one of the broad strategies that you will use data augmentation for working with fewer images, which is a very practical problem when you are trying to classify a new set of classes. Other strategies that I can take is that I can learn a better representation of images, which is basically the embedding based learning. And this will be the focus of today's talk. All right. Compare that to generative modeling, where I'm generating new images that look like the images that I wanted to work on before. We will not work on these kind of images for today's talk, but that involves, if you are interested, something called GANs, generative adversarial networks. And then there is a whole bunch of more advanced techniques such as meta learning, where you are learning to learn. So you are trying to solve many different vision problems together, and you are trying to see what meta algorithm works for all of them, so that you can uh, come up with a meta algorithm that learns faster with fewer images. Another thing that we can look at is regularization, which means that I will not, in simple terms, it would be that I will not have the weights of the neural network, take any value, but I will regularize them. I will constrain them so that I can learn from less data without overfit. So these are the broad strategies. Any questions? Okay. So the benchmark data sets that people compare their new techniques on are Omniglot dataset and Mini ImageNet dataset. These are two popular datasets. But then there are some other datasets also on which they can compare techniques. What Omniglot is that if you are familiar with MNIST dataset, in MNIST dataset you have 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are your 10 handwritten digits. right? And you could be given an image of any one of these digits, and you have to recognize it among one of these 10 classes. So omniglot is a generalization over that, where you have 1623 classes, and it includes uh, images of characters from 50 different alphabets, including the Roman alphabet, which has A, B, C, D, but also Devanagari alphabet, which includes like K, G, etc. Right? And also Bengali alphabet, and some of the other Indic languages such as Bengali and Telugu and so forth, but also languages from Africa and other places. So uh, it has 1600 characters from 50 different alphabets, and some of these characters have as few as 5 samples each. So it's really a few shot learning problem. So if I show you 5 different renditions of K, right, you should be able to learn from that what to recognize this letter K when I show this to you in a novel image. So that is one data set on which techniques are compared. The other data set is a subset or a variation of the ImageNet data set, where instead of 1,000 classes, we have 600 classes, and we have only 20 samples per class. And the image size is reduced to 84 pixels by 84 pixels and three channels, red, green, and blue. So these are the two data sets on which these tasks and on these techniques are compared. And the way they are compared is in C way K short manner. So what that means is that we will take C classes and see if we can, so C classes, for example, 20 classes, and if we give them only 5 examples each, 5 short, then can we learn from just 5 training examples? So that would be like a typical setting to compare a few short learning techniques. So the first thing that you might try for any few short learning problem is never start a neural network whose weights are randomly initialized, because that does not contain any prior knowledge of what natural images look like. So always start with a pre-trained network. Right? So always start with a pre-trained network. So this could be a ResNet 18 model or a ResNet 50 model or an Inception V3 model. Whatever that model is, the weights are already initialized to ImageNet dataset. ImageNet dataset is a very general dataset, has 1,000 different classes of objects. And when your network is already pre-trained on that, it has already learned to extract things that are important for recognizing shapes in natural images, such as edges, combinations of edges, etc., etc. So we will take away the last layer, because last layer uh, is should give you the output for your problem, and we will replace it with a new last layer. And one easy way to work with very few samples is fine tune just the last layer. Don't worry about fine tuning the lower layers below that. So what I mean by that is that you have an image, and then you have a conv layer, and then you have a pool layer, and then you have a conv layer, etc., etc. And then finally you have a flatten layer where you flatten the convolutional map, and then you have a dense layer or a fully connected layer. It's also called FC, fully connected layer. And you might have a few of these, and then you have a classification layer. So just replace the last layer, and this all the previous layers will be, except for the up to the first conv layer, these will all be pre-trained. These will be pre-trained on ImageNet. So you don't worry about where the weights of these layers come from. You just train the weights of the last layer. Right? So that's a form of regularization.
Right.
That means you are taking this, yes, you're taking this neural network and you're not letting it have the freedom of having any weights in the lower layers. Another regularization that we can do is that we can fine tune the lower layers, but we can put a penalty on the L2 norm of the lower layers, the weights of the lower layers. So what is L2 norm? It is also called weight decay if you look at neural network libraries. So these are some forms of regularization that you will start with when you have not many samples per image to train on. And then obviously you will do these augmentation, which is flipping the image, color jitters, props that I showed you uh, in that collab notebook. Right? And then you will have weight decays. That's a form of regularization that I talked about already. And then something called early stopping. It is very important to do that you monitor the performance of any machine learning system on a held out data set. And if it is overfitting on the training data but not performing very well on the held out data, then you stop training the model. So these are some of the basic steps that you will do. Now let's look at some more advanced steps. Uh, when you want to go beyond, let's say, just 50 samples per class, now you want to go to even smaller number of samples per class, just 20 or 5 samples per class. So one of the ways of doing that is to do something called metric learning. So what metric learning means is that instead of learning to classify objects, you are learning to extract features from images, such as these features are very useful in some sort of a metric sense, that they make some, you can compare these features in some way. A metric is basically a way of comparing two things. So you can compare these things in some way so that that comparison is meaningful or it is accurate in some sense. So one of the ways of doing that is to train a Siamese network. What that means is that you will take a test image and you will compare it against a reference image. Okay? So both of them will go, you will pass them through the neural network, and these convolutional filters will extract feature maps, and then the next convolutional features will extract the next features maps, and so forth. Except that this neural network and this neural network are exactly the same. They share the weights. They are just two copies of the same neural network. And then you may even have some fully connected layers here, FC layers, dense layers. Now, once you have extracted features from these feature maps, you will get a vector representation or a feature representation for both images. So this is for, so if this is x1 and if this is x2, then this is f of x1 and this is same f of x2. So same function, or I can call it f theta of x1 and f theta of x2, theta being the weights and the biases of the neural network. So the same function is applied to both images, but we get two different vectors, f theta of x1 and f theta of x2. All right. So so let's say, so what is the example of this feature? So let's say this is a feature which has a dimension of 512. So it is a vector of size 512 cross 1. Okay, whereas your image was, let's say, 224 cross 224 cross 3. Right? 3 is the red, green, and blue. 224 is the height of the image. 224 is the width of the image. Or if you have mini ImageNet, it will be 84 cross or 84 cross 3. Whatever that is, that image size is constant for both the test and the reference image. But you have extracted some 512 numbers from it, and that is your feature vector for that image. And the same neural network is replicated for both the test and the reference image, and it extracts the feature for the test image and the reference image. Now, what I want to do is I want to train this neural network using a metric so that these two images are either their feature vectors are either close to each other or far away from each other, depending on whether they are from the same class or they are from a different class. So a dog versus dog feature should be close to each other. A dog versus cat feature should be far away from each other. I can also use this for something like face recognition, where, for example, if I want to verify whether a person is claiming the person that he is. So let's say this person shows up his face, and I have and claims that it is Amit Sethi, and I have an image of Amit Sethi in my database, and I run this through some feature, through some layers of the neural network. I run the stored image also from the layers of the same neural network. I get one set of features, I get another set of features. I should be able to compare them, and I should be able to see whether these two features are similar to each other or not similar to each other. If they are similar within a threshold, then the person's claim is correct that he is the person that he's claiming to be. And if they are not close to each other, then perhaps they are not the same. The person is an imposter. So this will be we will show this in a demo for handwritten digits, but this can be used for faces. It can be used for any kind of biometrics. It can also be used for few short term. So the code snippet would be something like this. What I will have to do is run the same neural network, and so let's say the neural network is Siamese network, and I will give it the image 1. Then I will give the same network image 2. I will extract feature 1, feature 2, and then I can do whatever I want with these features, such as concatenate them and then use them for further processing. So what would be an example of these images being close or not being close? So let's say if I look at this I'm back here. So let's say I look at this 512 dimensional space. So 512 is just an example. It could be a different dimension also. It could be a 64 dimensional space. It could be a 124 dimensional space. Usually we use powers of 2 so that we use the memory efficiently. There is nothing sacrosanct about powers of 2 otherwise. So we will use, let's say, for example, 512 dimensions. So I have two numbers now. I have in a 512 dimension, I can only draw like 2 or 3 dimensions, but in 512 dimensions, I have 1 point and I have the other point. So this is f of x1 and this is f of x2 in this 512 dimension space. So what I can look at is what is the Euclidean distance between them. I can look at what is the angle between them and so forth. So these are different measures of their similarity or dissimilarity. So when I'm looking at angles, I will look at the cosine of the angle, and that cosine of the angle, if it is closer to 1, then these images are similar to each other. If it is closer to 0, then they are dissimilar to each other. If you remember your high school geometry, then in two-dimensional spaces, the largest cosine between two vectors is 1 when they are exactly on top of each other, and the lowest one is -1. But in high dimensional spaces, we don't deal with the -1 cosine when they are exactly in opposite directions. That is very, very rare. Usually we deal with those that do not fall in the same direction and are the orthogonal direction. So we usually do deal with dissimilar images having a cosine of 0 as opposed to -1. So many times we don't want to hard specify whether that similarity is 0 or 1, right? An example of that would be, let's say if your classes are the following. You have a wolf, you have a dog, and specifically you have a husky, and you have a cat. Obviously, the dog and the cat are very dissimilar, so we may not mind if the similarity comes out to be 0. But what about a dog and a wolf, especially a husky and a wolf? A husky looks very much like a wolf, so we may not want their similarity to be 0. We may not want their similarity to be 1 either. We may want it to be somewhere between 0 and 1. So there are the classification of natural objects when you have lots of classes, and especially when you have medical images, is not apples and oranges all the time, right? So there are objects, there are classes that are relatively close to each other, although they are separate classes. So for that, we don't want to specify a binary outcome of 0 or 1. We want relative outcomes between 0 and 1. So for that, sometimes we use something called a triplet Siamese, where we replicate the same neural network 3 times, 1, 2, and 3, and we give it 3 different images for both for training usually, not for testing. In training, we would give it a reference image and a positive image and also a negative image. So what that means, so this reference is also called anchor. So I'll call it A, and this is positive, which is plus, and this is negative, which is minus. So what that means is that the reference and positive image, they are closer to each other compared to reference and negative image. So we are looking at pair-wise comparison, not just pair-wise comparison, but pair-wise comparison. So in a normal neural network, you will give a single image at a time. In a Siamese in neural network, you will give 2 images at a time. In a triplet Siamese, you will give 3 images at a time, which form 2 distinct pairs. So the reference versus positive and the reference versus negative. Okay. So here what we want to say is that this feature, the distance between these two features should be less than the distance between these two features, or the similarity of these two features should be greater than the similarity of these two features. That's all we want to claim. We don't want to say that this similarity is 0 and this similarity is 1. That we don't want to give those hard constraints. So sometimes that turns out to be a better way of classifying a large number of classes. So basically, we have 2 ways of looking at the metric of comparison. We have the Siamese training and the triplet Siamese training. So in Siamese training, we have only 2 objects, either X reference and X positive, or X reference and X negative. So if you are looking at distances, then the distance between ref and positive will be low, such as 0, and the distance between ref and negative will be high, such as infinity or 1. If you are looking at similarity, on the other hand, it works as the inverse of distance. So between the reference and positive, the similarity will be high. Between the reference and negative, the similarity will be low. Okay, so these are hard metrics for a twin Siamese. On the other hand, if you are looking at triplet Siamese, then we'll look at 2 pairs or 3 samples at a time. So if you are looking at similarity, we will have X ref plus X positive. So their similarity minus the similarity of X ref and X negative should be greater than a margin. Okay, so we are just saying that it should be greater than a margin. We are not saying whether it should be one of them should be 0 or the other one should be 1. Similarly, if you are looking at distance, then the distance between X ref and X negative minus the distance between X ref and X positive should be greater than a margin. Okay. So what is the loss function that we can use for such networks? We can use pairwise cross entropy or triplet-wise hinge loss. So these are some popular losses, but a lot of research is about coming up with better losses and so forth. So what is a pairwise entropy loss? Cross entropy loss. So if you uh, have looked at neural networks, you know that the cross entropy loss is something as simple as minus target value times log of output uh, minus 1 minus target value log of 1 minus output. So what this means is, let's say my output is whether what is the probability of an image being dog, right? So here we are not looking at pairwise images. We are just looking at a single image at a time. So the target value will be either 0 or 1. So if the image is indeed that of a dog, then I want this log of y to be minus log of y to be as low as possible, so that it comes close to the target value. Sorry, as high as possible, so that I can come as close as possible to this target value of 1. So I want to minimize this loss. Whereas if the image is not that of dog, then this 1 minus t will take over, and I will have only this effective term in the loss function. Now, this works very well when your t is either 0 or 1. So we can use the same thing for pairwise images, where we can say that I have minus t, where t is whether they are from the same class or not. So t is again binary, right? But I will take log of similarity between x plus or x test and x ref. Okay. And then I will have minus 1 minus t log of similarity between xt and xref. So that could be my training objective. So here t is 1 when they are from the same class, and t is 0 when they are from a different class. Okay, and the similarity function will be a cosine similarity. So if your xt or f of xt and f of xr, these are like 512 dimensional vectors. So basically, I will have xt dot product with xr, and I will divide it by xt norm of xt times norm of xr. So the regular cosine definition that we have from high school. Now this works for pairs, but when we are looking at triplets, right, then we use something called triplet-wise hinge loss. And the example of that is that I need now 3 images, all right, and for these 3 images, I need to define a loss. So what a hinge loss is, it's like a rectified linear unit in the sense that it is 0 on one side, and it it has a slope of 1 or minus 1 on the other side. So if you remember support vector machines, the hinge loss looks something like this, where it is 0 on one side, and it is minus identity on the other side, right? So something similar we can apply for pair of similarity, where whatever we want to be true. So let's go back here. uh, Here, what we wanted to be true was that this similarity minus this similarity is greater than a margin. Now, this margin is a positive margin. I can bring it to the left side of the inequality, and this will become a negative margin. And I bring it to the left hand side. And if I take the negative of the whole thing, then I can put it in the hinge loss, where when the condition is satisfied, then I get 0 loss. When the condition is not satisfied, I get a loss that keeps going up. So that is basically the triplet wise hinge loss. So these are some ways of training with a few samples for using Siamese networks. So if you understand Siamese networks, then the next 3 techniques build on top of that. So let's take some questions that you may have about Siamese networks. Okay. Any questions?
Hello.
Yeah.
Yeah, actually, I want to ask about the network, Siamese network.
Yeah,
We are replicating the structure of, like, we are passing the same image as an input twice. How do we say that we are not, like, what is the comparison between the Siamese network and a larger network which is having the more number of parameters layers like that? So what can be similarities or differences intuitively?
right. Okay. So first of all, we don't pass the same image twice in a Siamese network. We pass two different images through the same network. Okay, so we pass two or three different images through the same network. The network remains the same, the image changes. So the image is either a triplet of three images or it is a pair of two images. Okay, so that's number one. Number two is that the Siamese network does not give you a classification. So if you look at ResNet 18 trained for ImageNet, its final layer will be a softmax layer with 1,000 units because it wants to give you a probability mass function for 1,000 different classes. Okay, so Siamese network will will be based on something that takes away that final layer and goes to the pre-final layer. So the only difference, it can have as many number of parameters as a regular network except for the last layer. Okay, so the only difference will be that it will not have the last classification layer. It will have the layer below that, which is the ReLU layer, not the softmax layer, for example.
Okay.
All
Yeah,
right.
and
So let's say that the pre-final layer has 512 dimensions, and then the final layer has whatever C dimensions for C classes, right? So it will not have those C dimensional layer. It will just have that 512 dimensional layer, which is the features that we are extracted from the image.
okay, and about that similarities between where we when we are comparing the similarities between the features, like, is can there be any other possible direction of research for that instead of cosine angles and like uh, in terms of,
Euclidean distance, yeah. Instead
yeah.
of Euclidean distance and cosine between the 512 dimensional angle, there are other ways. So I will show some of those slightly later in the talk, where you have a very small, fully connected neural network to do that comparison that you are talking about. So that comparison, how to do that comparison, also need not be fixed. It can also be learned. So if you have just a cosine similarity, then it's a fixed function to do that comparison. Instead of that, that function itself can be learned.
Thank you so much.
Okay. All right. So if there are no further questions, let me continue. So if you
I had a
understood,
question,
yeah,
Amit.
yeah,
Is
yeah.
that is there a reason why a triplet-wise hinge loss would be particularly suitable for CME's networks?
Yeah, so the when your number of classes goes up, then the strict requirement that two classes are either similar or dissimilar, that becomes counterproductive to training the neural network, in the sense that it finds it too hard to separate all the classes together, as required by a pairwise separation. Whereas with triplet, it just knows that two images are either in the same class or not in the same class, so they are either close or further away, but they are not too, they need not be too far. So for example, wolves and dogs need not be too far from each other, so it finds it little easier to train the neural network to satisfy that inequality constraint as opposed to the equality constraint.
Thank you.
All right. Okay. So if you understand the Siamese networks, particularly the pairwise Siamese, then there are a lot of uh, variations on this theme that go in that have went on to define few shot learning in image classification. So one of the first one is a one-shot learning technique, which is called matching networks, and it's based on something called attention-based embedding. It's it's not that difficult a concept. It's just a slight extension of the Siamese framework. So here, what we have is, I mean, for confusion in the paper, they have two different neural networks, G theta and G phi and F theta. But in reality, in their own implementation, they just use the same network. So basically, let's say you have a test image X and a training image Xi, and you want to find out what is the label to be given to this image X, where you know the label that was given to the training image Xi was Yi. So what you do is you compare the two images using this comparison function A, right? And based on the comparison, whether the image is close to ith training image or the jth training image, you will use the weighted sum of their labels. So that's pretty much what it is. So if you have C different classes, you will take the test image and you will compare it against all the C classes. And if they are similar, then the weight of their label will be higher. If they're dissimilar, the weight of their label will be lower. And then you will take the weighted average of the labels. So that's pretty much what it is. And how this comparison takes place is could be using something like cosine similarity. So not that different from what we have seen before. Based on cosine similarity, the only difference is now that the classification scheme itself is based on the weighted average of the labels, and it can be trained using uh, n plus or C plus one images, C images from C different classes, and plus one image that you are training it to be close to one of the C classes, but not to the other ones, using something called something like a cross entropy of softmax, which is also used in regular neural networks. So what that means is that if you have C different classes or n different classes in this case, you will have these many source images and you will have a query image. So the way you will train is in each batch, you will have one image from each class plus one random image from one of the C classes. This F and G networks are not different. This is also F actually in reality. And you extract the features. So let's say this is 512 dimensions. This is also 512 dimensions. And then you are taking their cosine, and that cosine gives you a weight for that class. So if the cosine is 1, then the weight is high. If the cosine is 0, the weight is low, and somewhere in between. And so we will multiply, we will take the weighted average of all the labels, and that's how we will get the final label Y. So this is very good when you have only one sample from each class. It works out very well for one shot. Now, the next technique generalizes this uh, to more than one sample per class, and it's not very different from what you see here. So before that, let's quickly look at the code, a code snippet of that, what you would have in this particular image, in this particular technique, that you will have a for each support image, which means one sample from each class, you will you will compute its features, and once you have those features, you also have the features of the input image, and you will take here the dot product of the two in the preparation for computing the cosine. This is the numerator of the cosine, and then we will divide it by the inverse square root, which will give us the denominator of the cosine, and pretty much that's what we have. And we will train that using cross entropy. So cross entropy will give us 1 for the class where we have we want the maximum cosine, and 0 for all the other classes. So the generalization over having only one example from each class is a prototypical network, which reduces to matching networks if we have only one sample per class. So this is a few short generalization over matching networks. So here, the main concept was that instead of bringing each image close to all the other images of its own class, we will try to bring it to closer to the average of all the images of the same class. So that average is called the centroid or the prototype. That's all there is to it. And then again, it is trained using cross entropy. So what that means is, let's say we have 3 different classes, and here we have uh, 4 samples from one class, 5 samples from another class, 5 samples from another class. So these are 4 samples from one class, these are 5 samples from another class, and so forth. And now what is this dot representation? This is basically, let's say, that 512 dimensional space of the features that we extracted using a neural network. In that 512 dimensional space, each image will occupy a point in that 512 dimensional space. So these 5 images occupy these 5 black dots, and their average dot, or the average 512 dimensional vector, is this triangle, which is called the prototype. Okay. So we have prototype of class, let's say 2, this is prototype of class 1, and this is prototype of class 3. So now at test time, if I'm given an image, all I need to do is measure its distance from all 3 prototypes and see to which one is it the closest. And based on that, I can decide on what the class level should be. And for training, I will use the same principle, that if I have one particular sample to train on, what I will do is I will try to reduce its distance from the correct centroid, and I will try to increase its distance from the incorrect centroids using again cross entropy of the negative distance in some sense, right? So basically, what I do is I take these the way I compute these prototypes is by using the mean of all the samples that I have picked from one class, and then I have this one query sample that needs to be correct to the closer to the correct prototype and further away from all the incorrect prototypes. So I will compute its Euclidean distance from all the prototypes, and then I will take the log softmax over the negative distances and use cross entropy to bring it closer to the correct prototype and further away from the incorrect prototypes. So when I train, I can basically use in this some samples from each class and one sample on which I want to minimize this loss, that it comes closer to its own prototype and further away from other classes prototypes. So that's how the training will go uh, in iterations. And the last example is that of relational networks, which is just what Siddharth was talking about. Instead of just Euclidean distance or cosine similarity, I run all samples and the query image through the same network F, and I take the features of the source images and the query image, and I concatenate them into a giant feature. So if this is 512 dimensions and this is 512 dimensions, so that the together what I get is 1024 dimensions, and I send that through a few extra layers so that the similarity itself is tunable in an additional network G in addition to that network F, which turns out to be slightly better than just using a fixed similarity like a cosine similarity or Euclidean distance or negative Euclidean distance. So here, basically, you can just add a few more layers for that function G that can compute that similarity. So that's pretty much it for from the theory point of view of how these networks are can use fewer and fewer samples to learn to classify data, and the classification is now just based on the distance of the similarity from uh, an average training sample, and that can give you basically the answer for how to classify a test sample. Any questions before we go into the practical demo? Okay. Abhijeet, are you here? Looks like so my PhD student Abhijeet was supposed to give a demo, but he recently had uh, bad weather in his area, and I think his internet is not very stable, so he may not have been able to make it. So I can just take more questions if you have questions about this. So in the demo, what we can do is we can share a video of that demo. Let me see if I can share it right away. So he had implemented this not prototypical, Siamese networks for recognizing digits with few samples. And he had implemented it on the Jetson Nano with a Jetson Nano that is interfaced with the camera. And he showed an handwritten digit on that and showed how the Jetson Nano was able to classify that. But looks like Abhijeet couldn't make. So what I can do is I can share perhaps a video link after once he's able to do it. If there are no questions, then I can give you 18 or 15 minutes back. Okay. All right. Sounds good. All right. So thanks everyone. I hope this was useful. And once I have the video from Abhijeet, I can share it. Yeah. Thank you.
Thank you, Amit, for the session.
Bye everyone.
Thanks, Amit.
All right. Thank you. Bye.
It must be really late for you. I mean,
Yeah. That's
yeah.
fine. Thank you.
So thanks a lot for joining this and giving a very interesting talk. I learned something. I learned a lot from this. So thanks.
Thank you. My pleasure.
Okay. So Amit, should we stop the recording? And
Yeah, we can. Yeah. Thank you.
okay. Okay.